Alright, so today we will be, at the very least, starting our discussion on, organize my stuff here. It's just called some convergence lemmas. Alright, so first off, we suppose that f of x being a system of n formal power series n formal power series, I'm guessing each in n variables with each fix having the form of being the ith component of x minus the sum over alpha being at least 2 of some ai alpha to the x alpha being the sum of xi minus vi of x. And we've seen from a proof of the inverse function theorem, f is formally invertible with inverse theta of x, of course, being our collection of theta I to the x, with each theta I having the form theta I of x being equal to xi plus over beta now, having size at least 2, of b sub beta to the I times x to the beta, being xi plus ci of x. Now, suppose we have a real number r between 0 and 1, and consider we have a couple conditions here. The first one, which we call AR, states that a sub alpha to the I is bounded by r sub alpha minus 1, all to the size of alpha minus 1, not sub. That holds for all alpha. Sorry, one sec, it might crunch the mic a little bit here, but. And secondly, essentially stating the same condition for our b beta. And this is, of course, for all of our indices beta. And this brings us to a lemma that, first off, AR implies that f converges absolutely on a to the n, and likewise that BR implies that theta converges absolutely on a to the n. And we remark, our proof rather, we just have to see that the sum over gamma having size at least 0 r to the size of gamma is equal to 1 over 1 minus r to the n, power of our n, which is going to be finite. Lemma 2 is that AR, condition AR is the same thing as implies condition BR and vice versa. And of course they're obviously symmetric, so we only need to prove one way. So we show that AR implies BR by induction on the size of beta. So let be true for beta prime where the size of beta prime is less than the size of beta. Then each xi is equal to fi theta x, being of course theta I x minus phi of theta x. Then comparing the coefficients of x to the beta, we see that b sub beta to the I is the sum of coefficients of x to the beta in phi sub I theta x. Since, keep in mind this is all in the context of k being ultrametric, we can just show each x to the beta in phi sub I of theta of x satisfies our estimate of its coefficient, that is. Now, we have that phi of theta of x be written as the sum of elements alpha has a size at least 2 of a to the I sub alpha of theta of x to the alpha. And likewise, theta x to the alpha consists of theta 1 x to the alpha 1 through theta sub n x to the alpha n. One sec, I gotta refigure my thing just a little bit. So, a typical monomial term in theta of x to the alpha have the form product from I being 1 to n, the product from j being 1 to alpha 1, alpha I rather, being our b to the I sub phi sub I comma j times x to the gamma sub I comma j. I called gamma phi before, I don't know what was up with that. And we want terms with the sum of the gamma ij's being equal to beta. Then we have the estimate of the product of coefficients by the product over I and j of r to the size of gamma of I comma j minus 1 being equal to r to the size of beta minus the size of alpha. Then since we have the size of each a sub alpha to the I is at most r to the size of alpha minus 1, we get the estimate of r to the beta minus 1 for the coefficients of x to the beta in phi sub I of theta x of x. And this just comes with a quick corollary. AR implies that F is an analytic isomorphism of AN onto AN. If you recall, that's something we were aiming to show last time. Maybe it was last video actually. It was some time ago we wanted to show this. And so by our second lemma from this video, we have AR and BR. Then by first lemma, for x in alpha a to the n, we have that x is phi composed with theta of x is f theta of x is also equal to theta composed with f of x, which is theta of f of x. So we now have a really big, scary chapter we're going to get through. Probably going to take a couple videos, but we will start it off today. I think it'll take at least a couple videos anyways, so this is on applications of filtrations on standard groups. All right. So start things off with a theorem. For each n being a positive integer, there exists a capital N in positive such that any finite subgroup of the general linear Lie group in n dimensions over Q over, that's supposed to be our rationals, of course, has order at most n. And proof, step 1, we show first off that this holds on ZP. This is, of course, being the p-adic integers. So first off, by a previous theorem, there exists an open subgroup say U of our general linear Lie group of n rank n over the p-adic integers such that U contains no non-trivial finite subgroups. Then if H is in the general linear Lie group of rank n over Zp is finite, is a finite group H must be in GLN of Zp over U, and the order of H must then be less than n, with n being the order of GLN of Zp over U. And secondly, we reduce to case 1 by 2 methods. First off, let H be a finite subset of GLNQ. And we're going to then let P be prime, and we extend H essentially. We take H to be transferred over to GLN of the p-adic numbers. Just keep in mind the rationals occur as a subset of the p-adics. I mean, the p-adics are just a certain kind of completion of the rationals, so there's an injection of the rationals into this, and so H can be carried under that. Then H is compact, so it has, we saw it has a conjugate in GLN of the integers, which is a different subset of the p-adic numbers. So the size of H is at most n as above. Alternatively, we're going to take, first off, take the previous appendix, which was what we started this video off with K being the rationals, giving us the evaluation ring of the integers. Note, well, first off, let L be a lattice in Q sub n. What is, sure. Oh, I get it. Then the subgroup, I think, okay, I'm not 100% sure. I'm pretty sure though that this should be Q to the n. Then the subgroup of GLN of Q, sending L to L, is a conjugate of our integer general linear group over of rank n. I guess is not necessarily Lie in this case. If H is a finite subgroup of GL and Q, there exists a lattice M sent by H onto itself. And we have part one we already showed. We have A by appendix 1. For part B, we can let L be a lattice any, and define M as the lattice generated by sigma L for sigma in H, which we know H is a finite set, so this is a finite set of lattices. This gives part B. So now by part A and part B, we see if H is a finite subgroup of GLN of Q, it has a conjugate in GLN of Z. So we can consider finite subgroups of GLNZ. We can then, of course, carry such a subgroup into the p-adic integers. I forgot the L. We are done. Now we can estimate n explicitly, that is, because we had n before be the size of GLN of the periodic integers divided by some arbitrary u. We can estimate n by taking GCDs of the estimate at each prime p. Looking at the page. So first off, if p is odd, then 1 is greater than 1 over p minus 1. The only primes we can fail for is 2. So we're going to let u be equal to what we call g1. To be the set of y, where y is 1 plus x. X is a collection of xij's, so a matrix of xij's, where each xij is in our maximal ideal of our valuation ring. Then we have GLN of zp over u is just GLN of our finite field with p elements. Then the order of GLN FP is the number of distinct sets of ordered bases in F, or FP to the n, which is the product of p to the n minus p to the I, from I being 0 to n minus 1. So it's pn minus 1 times pn minus p times pn minus p squared, and so on. Now, in case 2, where p is, well, the only other option is p being 2, then we have to loosen this to 1 over p minus 1, since that 1 over p minus 1 is exactly 1. So we're going to let u be g2. Then GLN of the periodic integers over u is GLN of z over 4z. Okay. We have an exact sequence, and of course we have the map from 0 to, we write it as 2z over 4z. Well, that is going to be distinct from z over 2z in its multiplication table, and squared being sent to GLN of some z over 4z being sent to some element of GLN of Z over 2Z, being sent to 1. Hence, the number of elements in GLN Z over 4Z is then two n squared times 2 to the n minus 1 times the product from of 2 to the n minus 2 to the I, from I being 1 to, of course, n minus 1. Now let's let n be equal to 2. For a case where p odd, well, we know the number of elements is p squared minus 1 times p squared minus p, which is p minus 1 squared times p plus 1. Then, well, first off, p squared minus 1 is congruent to 0 mod 8. So we have that p squared minus 1 times another even number, p squared is namely p squared minus p, must be congruent to 0 mod 16. In this first equation, you just plug in p. In this case can only really be 1, 3, 5, or 7. And you can just go in your head to calculate that this is always true. You can just multiply by an even number. And secondly, we have that 1 of p minus 1p and p plus 1 must be divisible by 3, so this all is congruent to 0 mod 3. Thus, we have that the order number of elements is congruent to 0 mod 48. When p is 3, we get 9 minus 1 is 8, times 9 minus 3 is 6, is 48 exactly. And secondly, when p is 2, then we likewise get that the number of elements is 2 to the power of 2 to the power of 2 times 2 squared minus 1, which is 3, times 2 squared minus 2, which is 2. So that is 96. Oh, my chair's squeaking too. And we get this, our best estimate for the order of finite subgroups of GL2 of Q is 48. But we can actually improve this. Next, note that any finite subgroup of GL2 over our rationals is in the set of matrices of determinant plus or minus 1, which is going to be our G0. We have an exact sequence where we send 1. Obviously, it's going to go easily into a special linear algebra, special linear group over Q into our G0, which we can then send to the sign of that matrix, which we then send to 0. So, for an estimate of the order of finite subgroups of G0, we can multiply the estimates for SL2 of Q by 2. Okay, where am I going to end this off? Alright. Then we will show, first off, every finite subgroup of SL2 of Q is a subgroup of a rotation group and is therefore cyclic. And we note once again, notation error, big fan of that. Secondly, only cyclic groups of order 1, 2, 3, 4, and 6 occur in SL2 of Z. Let's look at the proof. Number 1. Let H be SL2 and the rationals be finite, and B be any positive definite bilinear form on the integer squared. We're going to let b bar of x comma y be the sum over sigma and h of b sigma x sigma y. Then b bar is positive definite and h leaves b bar invariant. Since the elements of h have determinant 1, h is a subset of the rotations of r squared with respect to the scalar product b bar. Now for part 2. We're going to let alpha be an element of finite order in SL2, I'm guessing, of Q. We pass to the complex numbers and put alpha in Jordan canonical form. Well, case 1 is where alpha is of the form mu 1 0 mu. Then alpha does not have finite order. Case 2, which is the only other case and so must be true, is that alpha has the form of some mu 0 0 some nu. Let n be the order of alpha, which, as you recall, is the power of n, smallest positive power of n. That brings us back to the identity. Then mu to the alpha and nu to the alpha is 1. So mu and nu are roots of unity. We also know that mu and nu lie in a quadratic extension of the rationals as they satisfy the characteristic, oops, don't know why I did that, the characteristic polynomial of alpha. If either of mu and nu are not in Q, they are both not in Q and are complex conjugates. I'll just write it out because I think using the bar would be ambiguous in this setting. Hence, either, well, first off, mu is new is 1, and they're either, and they are positive or negative 1. Secondly, mu is a primitive nth root of unity for n greater than 2, and nu is its conjugate. Since the nth cyclotomic field is of degree being phi of n over the rationals, with phi being Euler's totient function. Phi of n is 2, so n is 3, 4, or 6. And I think we're going to call it there. Yeah, next time you know what? No, there's a delineation at the bottom of the page. There's a demarcation. So let's go a little further. So we want to find here an explicitly an element of order 4 and order 6 in SL2 of Z by considering a quadratic extension of the rationals. I'll write this out. We have explicit elements of order 4 and 6 in SL2Z by considering a quadratic extension K being Q extended by X and representing multiplication by X using our basis 1 and X. So, for element of order 4, take X to be a primitive fourth root of unity. Then multiplication by X as order 4 and matrix being 0, -1, 1, 0. And order 6 is the same case, taking, of course, being a sixth root of unity and being having multiplication order 6. In this case, we have X being 0, -1, 1, 1. And next time we're going to finish off this appendix. Yeah, we got 2 pages. We'll finish off this appendix and then we'll move on to Bourbaki, I guess. Yeah, thanks for watching.